Hi everyone, I hope you are doing awesome. In this video, I'm going to explain the knowledge distillation and a student-teacher learning paradigm and implement one of the knowledge distillation techniques using PyTorch. The increase in the size of neural networks driven by advancements in data availability and computational power has led to large neural networks showing remarkable performance and ability to handle complex tasks in various domains. Although these large models achieve profoundly great performance on many tasks, they are not suitable for deployment in environments with limited computational resources. Knowledge distillation is an approach for compressing large, complex neural network models into smaller ones, facilitating faster and more efficient deployment in resource-constrained environments while retaining crucial information. Okay, what's knowledge distillation? As mentioned earlier, knowledge distillation paradigm aims to transfer the knowledge of a large complex neural network to a much simpler and more efficient one while the performance is almost preserved. The larger and more complex neural network is called the teacher. And through a set of mathematical operations called distillation, the knowledge within the teacher is going to be transferred to the student. In other words, the student is somehow forced to mimic the behavior of the teacher. Knowledge distillation was introduced in a paper entitled Model Compression for the first time in 2006. Later, in 2015, the paper entitled Distilling the Knowledge in a Neural Network, authored by Geoffrey Hinton, was introduced. The paper proposes a method to transfer the knowledge from the teacher model to the student model by training the latter to mimic the behavior and predictions of the former. This process involves leveraging the soft targets or probability distributions produced by the teacher network to train the student network, resulting in improved generalization, faster inference, and the ability to compress complex models into smaller, deployable ones. There exists a huge literature around this topic, and I'm going to cover many of them in my future videos. So if you haven't still subscribed to my channel, please subscribe to it and keep up. In the rest of this video, we focus on explaining and implementing the paper entitled Distilling the Knowledge in a Neural Network, authored by Geoffrey Hinton. In regular training of neural networks for classification tasks, the input is passed to the model and the model projects a probability distribution over the class labels. Neural network weights are tuned by minimizing the cross-entropy loss function. The cross-entropy loss function forces the probability distributions produced by the model to get closer to the ground truth, which is another probability distribution over class labels. In the knowledge distillation paradigm, not only the discrepancy between the student's probability distribution and ground truth is reduced by minimizing the cross-entropy, but also the discrepancy between the student and the teacher probability distributions over the class labels is reduced by minimizing the Kullback-Leibler or KL divergence. KL divergence is a measure of how one probability distribution diverges from a second, typically used in information theory and statistics to quantify the difference between two probability distributions. It can be used to quantify the discrepancy between two continuous probability distributions as well as two discrete distributions. In conclusion, in the knowledge distillation paradigm, the student is forced to learn from the ground truth or hard labels by minimizing the cross-entropy loss function, as well as learning from probability distributions over class labels produced by the teacher model by minimizing KL divergence. To convert each model's output into probability distribution over class labels, it's essential to apply the softmax activation function on the model's output. The teacher's probability distributions are a peak over the correct class label and almost zero everywhere else in many cases. To soften the teacher's probability distributions, which are somehow hard distributions, the teacher's output can be divided by a variable t called the temperature before being passed to the softmax activation function. As the temperature increases, the model's probability distribution tends to resemble a uniform distribution more closely. In conclusion, in the knowledge distillation paradigm, the student learns from both the hard labels or ground truth as well as soft labels produced by the teacher and aims to align its distribution with the teacher's distribution. The intuition behind the effectiveness of this strategy is that the probability distribution over class labels produced by the teacher conveys vital information about the similarity and dissimilarity of samples within different classes. In learning from the ground truth, the model only learns that, for instance, a cat has this set of features or a dog has that set of features. In learning from the teacher's soft labels, the student learns about the features that different classes have in common. For instance, cats and dogs have lots of features in common, whereas they are very dissimilar from a frog. Or horses and deer have lots of features in common, but they are not similar to a bird. Teacher soft labels can be regarded as an additional source of information, providing valuable insights into the similarities and dissimilarities between different classes. Okay, let's jump into code and implement the approach for knowledge distillation proposed in the paper entitled Distilling the Knowledge in a Neural Network, authored by Jeffrey Hinton. Some necessary modules are imported in cell 1. Some hyperparameters are set in cell 2. We are going to use MNIST dataset, so the train and test splits of MNIST dataset are downloaded here. We define a class for the teacher model. The teacher model contains two convolutional layers, one max pooling layer and one fully connected layer. Output feature map of the conv1 has 256 channels. Output feature map of the conv2 has 512 channels. In forward method of the teacher model, useful features are extracted using convolutional layers, and the fully connected layer is used as a classifier that learns the mapping from extracted features to the class labels. The student model has the same architecture as the teacher model, whereas it has way less parameters. In a student model, output feature map of the conv1 and conv2 has only 8 channels. In training without the knowledge distillation, in each epoch, we should loop over the dataset, move features and targets to chosen device, perform forward pass and compute cross-entropy loss function between model's probability distribution over class labels and the ground truth. Then perform backward pass, compute the gradients, and update model weights by performing optimizer step. In training with knowledge distillation, the procedure is the same as training without knowledge distillation, except that the loss function in this case is a linear combination between cross-entropy loss function and the KL divergence between a student and teacher probability distributions. We need to define a function for getting the accuracy of a given model on a given split of the dataset. We don't need to keep track of gradients in this function, so we wrap it in torch.nograd. We loop through the dataset, find the predicted class label for each input sample by the model, and divide the total number of correct predictions by the number of total samples. We need to define a function to get teacher's probability distribution over class labels. We should get the teacher's output and pass them to softmax activation function. And since we don't need to keep track of gradients in this function, we wrap teacher's forward pass in torch.nograd. Then we instantiate one teacher model and two student models, which are completely initialized equally at the beginning, and we define an optimizer for each model. We can print the norm of the conv1 of a student 1 and a student 2 to make sure they are initialized equally. Let's print the number of parameters within each model and the ratio of a student's parameters to teacher's parameters. Okay, we're almost done. We can train and test our models with previously defined functions for training and testing procedures. If you have any questions, please ask in the comments. I'll answer all of the questions. Well, as you can see, a student trained with knowledge distillation achieves about 0.2% higher accuracy and performs better than the student trained without knowledge distillation. Thanks for watching. I hope you find this video informative, valuable, and educational. If you like this video, please subscribe to my channel.